This diagram shows the fuel system of the V2500 power plant, and you can see the relationship of the FADEC with other components of the system. The FADEC controls the supply of fuel to the engine through the fuel metering unit, FMU. Fuel from the fuel tanks enters the system through a low-pressure fuel shutoff valve. This valve is normally opened or closed by movement of the associated master switch. However, it is commanded closed if the fire push button is released. The low-pressure pump moves the fuel to the integrated drive generator cooler and through the fuel oil heat exchanger, where the lower fuel temperature is used to cool the engine oil. This process also exchanges sufficient heat to keep the fuel from icing. After the fuel is filtered, it passes through the high-pressure pump, where the fuel pressure is raised to levels necessary to atomize the fuel for proper combustion. The fuel metering unit, FMU, provides some of this high-pressure fuel to operate actuators on the components shown on the left, while the majority of the fuel is delivered through a fuel flow meter to the combustion section of the engine. Fuel flow information is displayed on the aicm. The FADEC operates 3 idle modes when the thrust levers are in the idle detent. These modes are the modulated idle, approach idle, and reverse idle modes. Modulated idle occurs on the ground when reverse is not selected, or in flight when the flaps lever is at 0. In the modulated mode, the idle speed depends on the demand from the bleed system and the ambient conditions. Approach idle occurs in flight when the flaps are not set at 0. The approach idle speed is higher than normal idle to allow the engine to accelerate rapidly from idle to go-around thrust. The approach idle speed is regulated according to aircraft altitude. The reverse idle mode is selected on the ground when the thrust lever is in the reverse idle position. The reverse idle speed is a slightly higher value than forward idle thrust. IDG cooling is fully automatic, and you will rarely be aware of its operation. Even so, in the next few frames we show 4 diagrams so that you can view the flow of fuel under different conditions. The first diagram shows the IDG cooling in the normal return to tank mode. It operates when low-pressure fuel flow is used for IDG cooling and high-pressure fuel flow is not used. The next diagram also shows a return to tank mode, but this mode diverts the fuel flow and utilizes high-pressure fuel flow to boost the overall flow through the system. This configuration is set when the IDG oil and fuel limit temperatures cannot be maintained within limits by using the normal return to tank mode. During periods of high engine speed that result in high fuel flow, or when fuel tank temperature is high, the fuel is not returned to the tanks. In this situation, the no return to tank mode will operate. This frame shows an example of high engine speed. Notice that a closed loop results, and all fuel is delivered to the engine, and no fuel is routed back to the tank. This frame shows an example of low engine speed and high IDG oil temperature. This is also the fail-safe mode. Notice how the high-pressure fuel flows in the reverse direction through the IDG cooler from the previous diagrams. The use of high-pressure fuel provides increased cooling volume through this cooler when the fuel consumption rates are low.